Hello everyone, hope you all are doing good. I am Anjana from Learnohub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we will be discussing ICSE Class 9 Physics Chapter 8 Propagation of Sound in a Medium. We have started this chapter before. We have discussed the production and propagation of sound. We will be continuing it today in this session. We will also be discussing the factors not affecting the speed of sound, infrasonic, sonic and ultrasonic sound waves. Are you ready for the session? Let's begin. Speed of sound in steel is more than in air. We'll take an example. If sound is produced at one end of a very long steel bar, two sounds are heard at the other end. Okay, take the same example of a desk. Okay, you're tapping on the desk. Two sounds you will be hearing. One is that which travels through the desk and the other is that which travels through air. Same case. A sound that is produced at one end of a very long steel bar. Two sounds will be heard, one because of the motion, the sound waves motion inside the steel bar, and the second is traveling through the air. Which one will reach faster? In this case, the one through the steel bar, that is the speed of sound in long steel bar is greater than the speed of sound in air, which means the sound will reach up faster in case of a long steel bar compared to the sound that reaches our ear through the air. Okay. Second example, a person living near the railway track often presses his ear against the steel rail to guess whether a train is coming or not. Why this is done? So, in case of a steel rail, okay, steel, it is a solid. Okay, you will be able to hear the sound of the train. Okay, so normally when you stand on a platform, railway platform, you will be able to hear the sound. Okay, but if you place your ears on the railway track, okay, don't do this. But when you place your ears on the railway track, that is on the steel bar, you will be able to hear the sound much faster. Why this is happening? Because the sound, there will be vibrations produced because of the motion of the train. Vibrations will be produced, that is the particles inside the steel bar will be vibrating. Okay, these vibrations can reach the person's ears more faster than the waves, that is the vibration that is reaching through air. Okay, why? Because air is a gas and the steel bar is a solid. The speed of sound in solid is greater than the speed of sound in air. Okay, in a gas. So, we can predict where the train is, at what time it will reach. Okay, how much distance is there, how far it is. All this can be predicted just by keeping your ears on the steel bar on the railway track. Okay, steel track when you keep, you can do this. Okay, before you hear it normally, through the air, the sound of train, you will be able to hear the sound. Okay, even though the train is much far. Okay, at that time, you won't be able to hear the sound through air. You only be able to hear the sound that is through the railway track, that is when you keep your ears on the steel bar. The factors affecting the speed of sound in a gas. The speed of sound in a gas is affected by the change in. There are four factors on which the speed of sound depends, or speed of a sound in a medium depends. So, it depends on the gas, density of the gas is the first thing. Second is the temperature of the gas. Third is the humidity, and fourth is the direction of wind. Now, we will be discussing them in detail. How each factor affects the speed of sound. First one is effect of density. Speed of sound is inversely proportional to the square root of density of the gas. So, we know the relation speed of sound is equal to root of gamma p by rho. Okay, which means V is directly proportional to the root of 1 by rho, or V is inversely proportional to the square root of density. Okay, so what happens when density decreases? Speed of sound increases, or when density increases, speed of sound decreases. This is what inverse proportion means. Okay, so if you are comparing hydrogen gas and oxygen gas. Okay, so density of oxygen gas is 16 times the density of hydrogen gas. Okay, so the speed of sound in oxygen gas will be directly proportional to 1 by root of density of the oxygen gas. Okay, and speed of sound in hydrogen gas is inversely proportional to the root of density of hydrogen gas. Divide. What do you get? Speed of sound in oxygen divided by speed of sound in hydrogen is equal to root of density in case of hydrogen gas by density in case of oxygen gas. Okay, you are taking the reciprocal. Okay, taking the reciprocal, which means root rho by h, rho h2 goes upward. Okay, so this is how it is. Now, what is the relation? Rho O2 is equal to 16 rho H2. That is, the density of oxygen gas is 16 times the density of hydrogen gas. Okay, so here VO2, that is speed of sound in oxygen divided by speed of sound in hydrogen, is equal to root of rho H2 divided by 16 times rho H2. Rho H2 get cancelled. So, VO2 by VH2 is equal to root of 1 by 16, which means VO2 by VH2 is equal to 1 by 4. Root 16 is 4. Okay, which means VH2 will be equal to 4 times VO2. What does it mean? The speed of sound in hydrogen will be 4 times the speed of sound in oxygen if the density of oxygen gas is 16 times the density of hydrogen gas. Next is effect of temperature. The speed of sound in a gas increases with the increase in temperature of the gas. So, when temperature increases, what happens to density? Temperature increases, density decreases. We have studied this before. Okay, they are inversely proportional. So, when density decreases, what happens to speed of sound? There is a relation, speed is directly proportional to 1 by root of rho, which means speed is inversely proportional to the square root of density. So, when density increases, what happens to speed of sound? Speed of sound decreases. When density decreases, the speed of sound increases, which means with increase in temperature, temperature increase, density decrease, speed of sound increase. When temperature decreases, density increase, speed of sound decrease. So, this is a relation. Okay. Now, with every 1 degree Celsius rise in temperature. So, here temperature and the speed of sound is related. The relation is speed of sound V is directly proportional to the square root of temperature. So, this is a relation. Okay. So, with every 1 degree Celsius rise in temperature, the speed increases by 0.61 meter per second or 61 centimeter per second. Okay. And the relation is the velocity of sound at temperature T. Vt will be equal to the speed of sound at 0 degree Celsius plus 0.61 into the temperature T in degree Celsius. Okay, so when you do this, you will be getting the speed of sound at temperature small t. Okay, this is the effect of temperature. Let us take an example. What is the speed of sound in the dry still air at temperature for 0 degree Celsius, second 25 degree Celsius. At 0 degree Celsius, it will be equal to 330. That is V0 is equal to 330 meter per second. Now, we have to find at 25 degrees Celsius. Okay, so what is the relation? We have Vt is equal to V0 plus 0.61 into the temperature T. Here temperature T is equal to 25 degrees Celsius. Okay, now put the values. Vt will be equal to 330 plus 0.61 into 25. Okay, what is 0.61 into 25? 0.61 into 25 can be written as 0.61 into 25 into 100 divided by 100. So, 25 by 100. This can be cancelled. You get 1 by 4. Okay, so 0.61 into 100 is 61 divided by 4, which is equal to 1.61 sorry, 15.25. Okay, 15.25. On adding this, we get 330 plus 15.25. That is equal to, Vt is equal to 345.25 meter per second. So, this is the speed of sound in the dry still air at a temperature 25 degrees Celsius. Okay, understood what the change is? Here the temperature has increased by 25 degrees Celsius. For every 1 degree Celsius, 0.61 meter per second is the change in the speed of sound. So, next 1 degree Celsius, again this much. Okay, so we have a change by 25 degrees Celsius. That is why we are multiplying 0.61 with the 25. Okay, if it is 20, you have to multiply it by 20. Third one, effect of humidity. The speed of sound in air increases with the increase in humidity. So, when you take water vapor, the density of water vapor is equal to 5/8 density of dry air. Okay. So, what happens when density increases? So, here when the humidity increases, okay, when humidity increases, that is the moisture content in the air increases, the density is decreasing. Okay. So, what happens when density decreases? We know the relation V is inversely proportional to root of density. So, density decreasing means the speed of sound will increase. V would increase. Okay. So, here we can say that when you compare humid air and dry air, in case of humid air, what is that? The density is lower. So, lower density means what happens? The speed of sound will be higher. Okay. So, the speed of sound in humid air is greater than the speed of sound in dry air. Okay. Effect of direction of wind. The speed of sound increases or decreases according to the direction of travel of wind. For example, if a sound wave is traveling in this direction. Okay. Here there is a radio, a person is standing here, and from the radio waves are produced, the sound waves are traveling in this direction, and wind is also blowing in the same direction. Let us say V is the speed of sound wave and the speed of wind is W. Okay, which means the sound speed will increase. The speed of sound will increase because the wind is also blowing in the same direction. Then the speed of sound will be equal to V plus W. Okay, if the sound wave is moving in one direction and wind is blowing in the opposite direction, in that case what happens is the speed of sound will decrease. Okay, it becomes V minus W. V is the speed of sound and W is the speed of wind, okay, which is moving in the opposite direction. Then we will be having V minus W. So, V plus W and V minus W, the value will be in between these. Okay, so this is how you can calculate the speed of sound. When you take a musical instrument and if you are able to hear the sound, okay, the wind is also blowing in the same direction, then in that case, the speed of sound will be higher and you will be able to hear the sound faster. If it is in the opposite direction, wind is blowing in the opposite direction, what happens? You will be hearing after a long time because the speed of sound is less comparatively. Okay. So, we have discussed the factors on which the speed of sound depends. There are 4 factors. The first one is the density, second is the temperature, third humidity, and the fourth one the direction of wind. Now, what are the factors on which the speed of sound does not depend? 3 factors are first pressure, second the amplitude of wave, and the third one wavelength or frequency of wave. So, why does it not depend on pressure? So, we have a relation. The speed of sound is equal to root of gamma P divided by rho, and we are saying that the speed of sound does not depend on pressure. Why is it? So, what happens is when pressure increases, we know volume will decrease. Okay, according to Boyle's law, pressure is inversely proportional to volume. Pressure increases, volume decreases. Volume increases, pressure decreases. Okay, now There is a relation for density. Density is equal to mass by volume. Mass is a constant. So when volume decreases, what happens to the density? Density will increase. Yes, density will increase. So here you can see that the ratio P by rho will always be a constant. Okay, the ratio P by rho will be a constant. So this is the reason why the volume of a gas does not depend on its pressure. Okay, so the second factor is the amplitude of wave. So when the amplitude of wave increases or decreases, it does not bring any change in the speed of sound. And the third is wavelength or frequency of wave. So the speed of sound is independent of the wavelength or frequency of wave. So three factors on which it does not depend. Okay, comparison of speed of sound with the speed of light. So we know the speed of light is 3 into 10 raised to 8 meter per second, and that experimentally got value for the speed of sound is 330 meter per second. Okay, so what are the difference between the sounds, the speed of sound and the speed of light? So we know that the light waves, they can travel through vacuum. But what is the case of a sound wave? We have done the bell jar experiment. In the bell jar experiment, when air was removed from the bell jar, okay, using a vacuum pump, what happens? That is, when it decreases, the air content decreases, what is happening? The sound is becoming feeble and finally it is not heard, even though the bell rings. Okay, so here, what is the reason? Because the sound waves cannot travel through vacuum, but the light waves can travel through vacuum. Second point, the speed of light waves is 3 into 10 raised to 8 meter per second in air, which is about 1,000,000 times greater than the speed of sound waves in air. So when you compare the speed of the light waves and that of sound waves, this is 3 into 10 raised to 8 meter per second. The other one is just 330 meter per second. Okay, at 0 degree Celsius, it is 330 meter per second. Okay, next, the third point, the speed of light waves decreases in an optically denser medium. So when the light rays travels from one medium to other, that is refraction. Okay, so when you take a ray of light, it travels from a rarer medium to a denser medium. What happens is, it bends towards the normal. Okay, when light ray travels from a denser medium to a rarer medium, it travels away from the normal. Okay, incident angle, angle of refraction, all these things. Okay, so the speed of light, what happens is, because when the density is changing, what is happening? The direction is changing. Okay, therefore, the bending of light is changing and the speed is dependent on the density of the medium as well. So when density of the medium changes, the speed of sound waves also, the speed of light waves changes. Okay, next, the light waves are transverse, but this is not the case with the sound waves. Okay, now the light waves are transverse electromagnetic waves, while sound waves in air are longitudinal mechanical waves. Okay, so light waves are electromagnetic in nature, they are transverse in nature. Okay, what about sound waves? They are longitudinal waves and they are mechanical waves. Sound waves are transverse, or also sound waves are both transverse and longitudinal waves. Longitudinal mechanical waves, that is, we have discussed. Now when you take the ripples in water, there you have transverse waves. Okay, transverse waves. Guitar is producing transverse waves. So it can produce both the waves. In case of solids and liquids, they produce transverse waves, but transverse waves cannot be produced by the sound waves. Transverse waves cannot be produced in the case of the inside water. Okay, on the surface of water, it can produce transverse wave, but not inside water. Also, it cannot produce in the case of transverse wave, cannot be produced in the case of gas. Consequences of the large differences in the speed of sound and that of light. So we know that before rain, thunder is heard and lightning is seen. Lightning is seen first and thunder is heard later. Why? Because when you compare, the speed of the light waves is 3 into 10 raised to 8 meter per second, which is very much greater than the speed of sound waves. Thunder is sound. Okay, so in thunder, light is seen much earlier than the sound of thunder is heard, although they are produced simultaneously they are produced, but the time taken for the sound waves to travel will be greater, okay, compared to the light waves to travel. So light waves will reach us instantly, but sound waves will take some time. Okay, this is why there is a time gap. Second consequence, when the starter in an athletic event fires a gun, a spectator sitting at a distance hears the sound of fire A little later, while a smoke is instantly seen. So, smoke is seen and the sound of the fire is heard. Okay, smoke is seen first. Why? Because the speed of light, okay, speed of light is greater than the speed of sound. Okay, speed of sound. Okay, which means the light can travel faster. You are able to see the smoke first. Okay, but sound takes time to travel. That is why he hears the sound of fire later on. Okay, experimental determination of speed of sound in air. For this experimental determination, consider two places A and B. Okay, at high altitudes, and the distance, that is, they are at the same altitudes. The distance between them is, say, some 1 kilometer. Distance D is equal to 1 kilometer. Two observers are considered. One is at A and the second one is at B. Okay, they are given a gun and a stopwatch. Okay, with observer at A there is a gun and a stopwatch. With B also there is a gun and stopwatch. In this experiment, what is done is, first the gun with the observer at place A is fired. Okay, so then at that time what B should do is, B should start the stopwatch. Okay, he should start the stopwatch. That is, when the gun is fired, a flash will be seen. When the flash is seen, B will start the stopwatch. Okay, the observer at B will start the stopwatch, and then he will end it when he hears the sound. Okay, so there will be a time interval between this. Why? Because we know that the light travels a million times more faster than the sound. Okay, so here when the gun is fired, a flash is seen, B starts the stopwatch, and he ends it when the sound of the gun, okay, the firing of the gun, sound is heard, when that is when B stops it. Okay, so there will be a time interval T1. So we get a time interval T1. Okay, that is A fires the gun and B has a stopwatch. Now just the opposite thing is done. That is, B fires the gun and A is taking a stopwatch with him. So that time you will be getting T2 as the time interval. Okay, that is, B is firing. When A is able to see the flash, he starts the stopwatch, and then when the sound is heard, he stops it. Okay, so T2 is when B fires and A is the observer. Okay, so here T1 is the first time interval and T2 is the second time interval. So we can find the time. That is, time taken for the sound to travel can be calculated, will be equal to T1 plus T2 divided by 2. That is, we are taking the average. Means when you take the average, you can reduce the error due to the wind flow. Due to the flow of wind, there will be some errors. So the errors can be eliminated. Okay, so here we have got the time, we know the distance, and the speed can be calculated. Speed V is equal to distance divided by time. You will be getting in units of meter per second. Okay, clear? That is 1 kilometer is 1000 meters and time you will be getting in some seconds. Okay, so this is what happens. Now, there are other errors as well. So here the errors, when you take the average, the errors due to the wind flow of wind can be eliminated. But there are some personal errors as well. That is, when you do an experiment, there are chances that maybe A is noting the time. Okay, maybe the personal errors means that is, A will be noting a time, it will be actually 2 seconds. Maybe A will note it as 3 seconds. Okay, due to some carelessness. So there are chances of personal errors, or maybe there will be some temperature difference between A and the places A and B. Okay, there may be some humidity difference between places A and B. In all these cases, there are chances of errors. Okay, so when you take the average time, you will be getting approximate value. So by now we have understood what are sound waves. Now what are the frequencies of sound waves? So we know that we can hear the sound. Yes, so there is a range of frequencies in which we will be able to hear the sound, and this range is 20 Hz to 20 kilohertz. For humans, the range is 20 Hz to 20 kilohertz. That is, the sound waves which are of frequencies between 20 Hz to 20 kilohertz is what we are able to hear. Okay, now it can vary from person to person. It's not the same for every person. So while aging, that is, for a normal average person's age, when considered, the range is 20 Hz to 20,000 Hz or 20 kilohertz. Okay, Now, when a person starts aging, what happens is his range will decrease. Okay, he may not be able to hear up to 20 hertz. It may be just up to 12,000 hertz or 12 kilohertz. This may be the range. Okay, when you take the case of a small children, in case of small children, they will be able to hear up to 30 kilohertz or 30,000 hertz. So this is what we say. It can vary from person to person. Okay, so our ears are sensitive to only a limited range of frequency. Not every frequency we will be able to hear. There is a limited frequency and this frequency range is 20 hertz to 20,000 hertz. Okay, understood. Now, we have discussed the case of human beings. When it goes to different animals, it can vary. Okay, we have heard that dogs can sense earthquakes more before. Why? Because thus they can hear the sound waves of higher frequencies. Okay, in case of human ear, in the range that is 2000 hertz to 3000 hertz, this is where the ears can hear the sounds, that is even a very feeble sound can be heard. If the sound is in this frequency range, the human ear can hear this sound. Okay, so the sound of frequency in the range 20 hertz to 20 kilohertz, we call it a name which is called the audible sound or sonic sound. Sonic sound or audible sound. Now, when the frequency is less than this audible range, that is from 20 hertz to 20 kilohertz, we call it infrasound or infrasonic sound. Infrasonic sound. In case of infrasonic sound, the frequencies will be less than 20 hertz. Okay, and if the frequency is greater than the audible range or the sonic sound, that is above 20 kilohertz, we call it as ultrasound or ultrasonic sound. Ultrasonic sound, that is frequency greater than 20 kilohertz. Okay, so there are three types. One is infrasound or infrasonic sound, audible sound or sonic sound, and the ultrasound or ultrasonic sound. And we understood the range of frequency. Less than 20 hertz is infrasound and greater than 20 kilohertz is the ultrasound. Okay, now we have considered the case of human ear. So when you go to the case, when you take the case of different animals, they can hear even infrasonic sound. That is, they can produce and hear infrasonic sounds and ultrasounds. Also, there are animals which can hear and produce ultrasounds. Okay, this is why they can communicate in a way that the humans cannot understand the way of communication, because the range of frequencies is different in their case. There are some animals whose frequencies, they can hear sound waves of frequencies less than 20 hertz. Okay, there are some fishes which can hear from 1 hertz to 25 hertz range. Okay, then in case of dolphins, there is a range. In case of dogs, elephant, in all different animals, their audible range is also different. It is not that all organisms has the same range of frequency. Audible range is not always 20 hertz to 20,000 hertz. It is only in the case of human ear, it is 20 hertz to 20,000 hertz. When you take the case of different animal, they will be having different range of frequencies. Okay, they can produce and hear sounds of frequencies below 20 hertz as well as above 20 kilohertz. So the frequency ranges for hearing and speaking by humans and animals. So there are different objects given, that is all animals and human beings. There are different objects given on the left side, and the frequency range of hearing and speaking is given on the right side. So first, when you consider humans, so we'll start with humans. In case of humans, we have already discussed, which is 20 hertz to 20 kilohertz or 20,000 hertz. Now, when you compare it with bat, what is the range? 10 hertz to 100 kilohertz. 10 hertz we know is less than 20 hertz. Okay, and 100 kilohertz is greater than 20 kilohertz, which means the audible range of bat is higher than. Okay, it is from 10 hertz to 100 kilohertz, but when you compare it with human, it is just 20 hertz to 20 kilohertz. So bat is having an audible range which is greater than that of humans. Okay, next when you take the case of cat, for cat it is from 80 hertz to 60 kilohertz. Okay, 80 Hz to 60 kilohertz. That is also different compared to that of humans. Next, for dog, it is 20 Hz. Starting is 20 Hz itself, but they are able to hear up to 50 kilohertz, which means the audible range for dog is also greater than that of humans. This is why they can detect earthquakes and tsunamis more earlier than, because they are able to hear the waves of this frequency range, 50 kilohertz. Okay. Next, in case of dolphin, for dolphin, they are able to start, that is from 200 Hz to 150 kilohertz, they are able to hear. Next, a grasshopper, it is 90 Hz to 1 kilohertz, which is small compared to the humans. Okay. So, at least these things you can just remember. Very important is in the case of human, which is 20 Hz to 20 kilohertz. You can just study these two. Ultrasound and its application. So, we have discussed the different ranges. Infrasonic or infrasound is less than 20 Hz. Between 20 and 20 kilohertz, it is the audible range or sonic sound. And above that, it is ultrasound or ultrasonic sound. So, sound of frequency above 20,000 Hz is called the ultrasound. So, we take a medium, okay, in a medium, it travels with the same speed with which the audible sound travels, that is 330 meter per second. This will be the speed. Okay, so when you consider solid, liquids and gases, this ultrasound sounds can easily travel through the solids and liquids, but when it comes to the case of gases, the intensity will be decreasing. Okay, so these are the basic things you need to know about the ultrasound. Frequency about 20,000 Hz. Now, what are the properties of ultrasound? Ultrasound has all properties similar to that of ordinary sound. We know the properties of ordinary sound. We know the speed of ordinary sound. Similar properties is what ultrasound is also having, but the difference is that the frequency ranges. The frequency is higher. Okay, so when we know that what is the relation between frequency and wavelength? Frequency increases means wavelength decreases. Frequency and wavelength are inversely proportional. So when you take a wave of high frequency, its wavelength will be very low. Okay, now the first property, that is, there are two other properties apart from the properties of audible range of sound waves. Okay, so energy carried by ultrasound is very high. Why is the energy high? Energy depends on frequency. Okay, energy is equal to, there is a relation, energy is equal to h nu, where h is a Planck's constant, which we'll be discussing in higher classes. Okay, in 12th you will be studying about this. Okay, which means this is a constant, Planck's constant is a constant value. Energy is directly proportional to the frequency. Frequency, we know it can be represented by f or it can be represented by Greek letter nu. Okay, which means when frequency increases, energy should also increase. So, the ultrasound will be having higher energy because these sound waves are of higher frequency. Next point, the ultrasound can travel along a well-defined straight path. Okay, why? Because when you take the case of ultrasound, they won't be able to bend. They don't bend at the edges of an obstacle. Normally, the sound waves can travel in such a way they can bend at the edges of an obstacle. But when you take the case of ultrasound, they have a well-defined straight path and they do not bend at the edges of an obstacle. Okay, why? Because when you consider, we have said that they are of high frequency, which means low wavelength. Okay, low wavelength. And this is the reason why they always travel only along a well-defined straight path. So, these are the two important properties of ultrasound. Applications of ultrasound. Where does ultrasounds find their applications? The first application is bats avoid obstacles in their path by producing and hearing ultrasound. So, here you can see this is a bat and you can find an insect in front of the bat. Okay, so this is an obstacle. Now what happens is bats will be producing and hearing ultrasounds. These bats will produce ultrasounds. So this ultrasound, what happens is it will go hit the obstacle. Here the insect, it will go hit the insect. Then what happens when once it gets hit, it will return back. It gets reflected. Okay, the sound waves get ultrasonic, sound waves get reflected. We know the range of frequencies in case of bats is 10 Hz to 100 kilohertz, which is very much greater than the audible range in case of humans. Okay, so this reflected wave will come back to the bat. Okay, so the bat can calculate the time taken. Yes, how much time is there between the releasing of the sound waves, ultrasonic waves, and hearing the ultrasonic waves. Okay, so hearing the sound waves, it will calculate the time, and with this time, it will be able to find the distance of pet, the distance of the insect, at what distance it is, and which direction it is moving. All these the bat will be able to calculate. Okay, so this is the first application of ultrasonic sound. Second application, ultrasound is used for drilling holes or making cuts of desired shape in materials like glass. So, if you have a material like glass, you cannot use a axo blade or something to make holes in that. Okay, for that purpose, you can use a device somewhat like this. It will be producing the ultrasonic waves, and this ultrasonic waves can be used for drilling the holes and making cuts of desired shape. Any shape you can make the cuts on materials. Like if you have a glass, you can do that with this type of a device which produce ultrasonic sound waves. Now the third application, for cleaning minute objects such as the parts of watches and electronic components, ultrasonic sound is used. First, you will be taking a cleaning solution. Okay, for example, if you want to clean a watch is kept inside this cleaning solution. Okay, a watch is kept inside the cleaning solution, and then ultrasonic waves are passed. Okay, so when ultrasonic waves are passed, we know ultrasonic waves are having high frequency. Okay, they have high frequency. So when this high frequency waves pass through the solution, what happens inside the solution? It's the vibration, high energy vibrations are created. Okay, due to this high energy vibration, the dirt gets detached from the material. Now, for example, if it is a watch, the dirt gets detached from the watch and it gets cleaned. Okay, for this purpose also ultrasonic sound waves can be used. A fourth application, for detection of defects in metals, ultrasound is used. So here you can see ultrasound waves. This is a metal block. Okay, so through this metal block, what is happening? If there is no defects, okay, you can see the ultrasound waves are passing clearly. Okay, without deflection, they are passing. So here an ultrasound detector is kept. So if all the waves that is being passed through the metal block reaches this end, that is the ultrasound detector is able to detect all the waves, then we can say that the metal block is having no defect. So now consider this case. Here the metal block is having some defect. So here we are considering a metal block with a defect. Okay, so ultrasonic waves, ultrasound waves are produced. Okay, these ultrasound waves are passing through the metal block. What happens is, here you can see the waves are passing, here also waves are passing. But what happens when the wave strikes this spot? Okay, so here there is a defect. Okay, when the wave strikes here, what happens? It gets reflected back. Okay, it gets reflected back. Okay, so when you check the ultrasound detector, not all waves are reaching here, which means there is a defect in the metal block and we can find where the defect is. Okay, for this purpose also we are using ultrasound waves. Now the fifth application of ultrasound is for imaging the human organs. Ultrasound is widely used. So using ultrasound, we can get the images of human organs like kidney, liver, gallbladder, etc. Okay, so here ultrasonography is being used. Ultrasonography is a method of getting the image of a person's different organs using ultrasound. Okay, then you have echocardiography. Echocardiography is to get the image of a person's heart. Okay, to get the image of a person's heart, echocardiography is used. So this helps us to detect if there is some stones or tumors in a person's body. Using this ultrasonography, you can detect it. Okay, you can find these by taking the images of a person's different organs, human organs. Okay. Next, ultrasound is used in surgery to remove cataract and in kidneys to break the small stones into fine grains. So, we have said ultrasound is of high frequency and the high energy. The energy will also be high because energy and frequency are directly proportional. Now, what is cataract? Cataract is a disease that comes to the eyes. Okay. So, here what happens is a cloudy something is formed on the human lens. Okay. Human eye lens. What happens is the normal lens. Compared to the normal lens, some cloudy thing will be formed and the person's vision will decrease. There is a decrease in vision. So, he will be able to see everything somewhat blurred. Okay, so this is cataract. For cataract operation, ultrasonic sound waves can be used. Then the second thing where the ultrasonic sound waves is used is in the case of treatment to break the stones. In kidney stones can be broken down and into fine grains using the ultrasonic sound waves, because we have said they are of high frequency, vibrations is caused, the energy of these radiations, this ultrasonic waves are very high, and they will be able to break the stones into the small stones can be broken down into fine grains. For this purpose also we are using the ultrasonic sound waves. So the last application in sonar. Sonar is a abbreviated form of sound navigation and ranging. Sound navigation and ranging. Okay, it is used to detect and find the distance of object underwater. Ultrasound. These ultrasounds are used. So here what happens is, so here in this ship there will be a sonar. Okay. So here waves will be transmitted. So this is a transmitter. Ultrasonic sound waves are passing. Okay. Underwater ultrasonic sound waves are passing. So this is the bottom. Okay. Once it reaches the bottom, there is an obstacle. Because of the obstacle, what happens? Sound waves gets reflected back. Here there will be a receiver of the sonar. There will be a receiver. Okay. So here you can see the reflected ultrasound pulse. Bottom of the sea, when the the ultrasonic sounds reach the bottom of the sea, it gets reflected and it reaches the receiver. Okay, so from this you can calculate the time taken. So by calculating the time, we can then find the distance at which the obstacle is. That is, we can, in this case, you can find the bottom, where the bottom of the sea is, using this ultrasounds. Now the difference between ultrasonic sound and the supersonic sound. The ultrasonic is used for ultrasound, while supersonic is used for objects which travel with a speed greater than the speed of sound in air. So ultrasound, we know the audible range is 20 Hz to 20 kHz. Okay. So above 20 kHz, we call it ultrasonic or ultrasonic sound. Okay. Now we understood what is ultrasonic sound. Now when you take the case of supersonic, it is not related to frequency. If we know that the speed of sound in air is taken as 330 meter per second. Okay. If some particles or object is moving, okay, object is moving with a speed greater than the speed of sound, okay, we call them supersonic. Supersonic. For example, fighter jets, fighter planes, okay, jet planes, all these are examples of supersonic objects. Understood? So ultrasonic and supersonic is never the same. Ultrasonic is, we are telling it related to frequency. Greater than 20 kHz, we call it ultrasonic. And the supersonic is related to the speed. Greater than 330 meter per second, we call it supersonic sound. Clear? We'll take an example. Second example, a bat can hear sound of frequencies up to 120 kHz. Determine the minimum wavelength of sound which it can hear. Take the speed of sound in air to be 344 meter per second. Okay. Now, we are given the frequency F. Frequency F is equal to 120 kHz, which is equal to 120 into 10 raised to 3 Hz. Next, what is given? The speed is given. V is equal to 344 meter per second. So, what is the relation? Speed of sound is equal to frequency into wavelength lambda. Okay. So, what we need to find? We have to find the minimum wavelength of sound which it can hear. Okay. So, we are given the frequency and the speed. We can find lambda. Lambda will be equal to V by F. Here, V is equal to 344 meter per second. So, lambda is equal to 344 divided by 120 into 10 raised to 3. Here the unit is meter per second. Here the unit is hertz. So, we will be getting lambda to be equal to, when you calculate, 2.87 into 10 raised to minus 3 meters or 2.87 millimeters. So, this is the wavelength lambda, minimum wavelength lambda we have determined. Third example, ocean waves of time period 10 seconds have wave velocity 15 meter per second. Okay, so find the wavelength of these waves and then the horizontal distance between a wave crest and its adjoining wave trough. Okay, so here you are able to see the time period is given. Time period t is equal to 10 seconds. Velocity, wave velocity v is given, which is 15 meter per second. We have to find wavelength. We have wave velocity is equal to frequency into wavelength lambda. Okay. Now, what is frequency? Frequency is 1 by time period, which means wave velocity is equal to 1 by time period into lambda. So, first we have to find lambda. Lambda will be equal to wave velocity into time period t. Okay, put the value. Wave velocity is 15 meter per second into time period 10 seconds, which is equal to 150 meters. Lambda is 150 meters. Now, we have to find the horizontal distance between a wave crest and adjoining wave trough. So, here when you consider a wave, this is a wave. Here we have a crest, here we have a crest, here trough, trough. So, this distance we have to find. We know this total distance is lambda, wavelength, which means the distance from a crest, horizontal distance from a crest to trough will be half of it, lambda divided by 2. Okay, we have found what is lambda. Lambda is equal to 150 meter, which means the distance between, horizontal distance between crest and adjoining trough is equal to 150 meter by 2, which is 75 meters. 75 meters. Okay, fourth example. The smoke from the gun barrel is seen 2 seconds before the explosion is heard. If the speed of sound in air is 340 meter per second, calculate the distance of observer from the gun. State the approximation used. So, here time is given, t is equal to 2 seconds. Okay, speed is not, speed is equal to 340 meter per second. So, this is the speed of sound. Here we are making an approximation that the speed of light is negligible compared to the speed of sound, because we know speed of light is 3 into 10 raised to 8 meter per second. It is high very much high compared to the speed of sound. Okay. So, here the speed of sound, that is the sound take 2 seconds to reach the person, but we are considering that the light will reach instantly because speed is very high. Okay, then what is the distance? Distance will be equal to, if speed is distance by time, then distance will be equal to speed into time. Okay, that is 340 into 2 equal to 680 meters. So, 680 meters is the distance. Okay, distance of the observer from the gun is equal to 680 meters. Hope you all enjoyed the session. I'll be back in the next session. Until then, stay tuned to Learnohub. Learnohub free hai, par best hai. Thank you.